We're very happy to have Vincent Calvez here to tell us about chemotaxis and some accelerating functions.
Morning, everyone. So let me maybe recap what was said last Friday. So for me, the main question is, first, before going to result, is how to describe waves when motion is persistent instead of Brownian. So sometimes it is called piecewise deterministic Markov processes, but in my case it will be as you saw a very simple occurrence. So it's just x dot equals to v, and at random exponential time, you have v, which let's say v some speed before change with this one, which is drawn from probability. Okay, so you are given a probability distribution function, probability density function m of v, and as I said, as an example, you can think of m of v being either uniform on some interval or a Gaussian. So in this case, v is bounded, your velocity space, and in this case, of course, v is a whole line. So these two things are the main objective of this lecture. And what it looks like, so you have a straight motion, and at some point, which are distributed exponentially, at some times, you have a change of direction. Okay. And you can have branching in addition to motion, to persistent motion, but this will not be the focus of today. So for today, I will sort of ignore branching and focus only on, let's say, on the statistics of motion. And more interestingly, I'm interested in the large deviation of such kind of process. And as you will see, it will depend very much of of course, on the shape of M, but more importantly, on which support M is, on which interval M is supported. Okay, and again, this is a 1D results, but it can be extended to higher dimension without too much differences. There are some technical details, so this is why I prefer to focus on 1D, but in spirit, it's okay. So the PD for the density of particles is a PD in the velocity, in the phase space, where you have position and velocity, and you have transport at speed v, of course, by definition, and then you have m of rho tx, which is the spatial density minus f. Rate of change is 1, and again you can have growth, logistic growth, but I will not insist too much on that today. Okay, so what so is that for which you can have, there was some reference by Fadjonato and colleagues, where you have a large deviation principle with rate function, which I will not write again, but just let me remind you that it's something which depends on x on some mu, which is such that you have x of t or trajectory, which is initial data plus the integration of, this is for the finite state space in their paper, but I'm pretty sure it can be extended to a continuous and compactly supported velocity space at bounded, which here you have a sum of velocity. Let me call it the sum because in my setting it's continuous. In there, in these references, it's a finite state space of finite velocities, finite number of velocities. But it's at least for the analogy, it's for the sake of analogy, let me consider to be the same. And you have the velocity, and you have a mu v of s ds, and this mu is a probability such that the sum of mu v is 1. Okay, so you have your rate function depends, of course, of your curve, but on something which is not the speed, but something which is related to the speed is how you average velocity to make a speed. Of course, this is the average velocity. So it's the velocity of the curve, which is average. And what you have to minimize is over the possible averaging you make. So it is how you make an average velocity. So this averaging will be is of course very important, the core of this rate function. And it's also something that occurs on the PD side. So what is the PD counterpart of this large deviation principle? How we see it is to look at the asymptotics of f, so of ft x v, and you have to rescale tv in the new units of time, which are t prime over epsilon, x prime over epsilon, which means that you are looking far away and you are for a long time, and you are doing this specific scaling, which is adapted to this problem. And then you say that what I mean by asymptotics, I mean that you are looking for f, loosely speaking, which is an exponential of minus u of t x v over epsilon. Okay, so you are looking in the new units of time and space, and you are looking at the exponential tail of your density, which looks like you are looking very far away, and very far away, very likely your density of particles will be like that, and you are looking into this, what the tail looks like. Okay, so this is the point of view I have. And if you do that, and if you write the PD for you, which PD for you, you just have to make this this transformation into your equation, and what you get is, so it's a logarithmic derivative of f. So it's minus, you just simply divide this equation by f. If you divide by f, you will get the logarithmic derivative of f. So with the new units and this epsilon, this just cancels. So it's epsilon 1 over epsilon d u epsilon over dt minus epsilon 1 over epsilon d u epsilon d, sorry, there is a v missing, dx. Okay, there is one epsilon due to the fact that I rescale time and space. So this makes an additional epsilon here in my new units. Okay, and because I'm looking at the logarithmic derivative with the 1 over epsilon, this exactly compensate this one and this one. And the right-hand side is almost unchanged. I have divided by v, so there is a, by f, so there is a -1 here. And the complicated term is this one, it's the m of v. And then I have the integration over v of exponential of space. So it's rho is the integral of f in v. So I will have u epsilon tx v prime minus u tx v dv prime. So this is rho divided by f. I think the sign is not correct, so it's a minus and a plus, because I divide by f makes a plus 1. Okay. So now if you, okay, these 2 points are related. You should just forget about that and just look at this PD from without almost no, and of course, the most important thing, sorry, I'm really, you divide by epsilon, because it is what you are looking for. Okay, so if you believe this is a correct, and that's, of course, this is just a reformulation of this PD with these units of time and space and this particular shape. So if you look at this PD, if you know nothing about PD, and you look at that, what do you see? There is no epsilon there. There is just du over dt. Fine. If du over dt means something, it is there. There is v du over dx. No epsilon there. There is one epsilon here. This one you have to be cautious about because this one will get small. Okay. And it's even worse. It is 1 over epsilon inside an exponential. It's terribly. It can be. This one can be terribly bad. And this one, of course, is okay. So if you think, if you believe that U is a good guy, is a good guess, then you would like this to equilibrate this. So -1 is fine. So it means that this has to be handled. Okay. So what does it mean for this to be bad? It means that this inside the exponential is positive. Because if this is positive in the numerator, you divide by epsilon, this is terribly bad. So the only possible way for this guy to be reasonable enough is the following. So you have a constraint, which is that U epsilon T xv minus U epsilon T xv prime. I would say constraint on the limit as epsilon goes to 0. If this limit makes any sense, what should it do? So if you should take the limit and you have 0 here. If you think it's a good approximation and that the limit makes sense, clearly this must be non-positive, okay? Because again, yes, it's a good sign. If this guy is positive somewhere and you have uniform uniform limit, which is actually the case, then you will get something positive to the epsilon. This term will be extremely large, and you will be in trouble. So this is a constraint which is natural in this analysis, and this tells you that, and this is for all v and v prime. It says this tells you that for all v and v prime, u is less than u0 tx and v prime. Okay, the same. So it tells you exactly one thing, that u does not depend on v. Must be like this. Okay. Under this constraint, and again, this constraint is what makes you happy here in this analysis. Okay. So then this is a theorem that all what I said on the formal level is actually correct. So under some technical conditions which are okay for M, which is the uniform distribution on an interval, on a finite interval. What I mean by technical condition, for example, if M vanishes on the extremity of the interval, you might be in trouble. So, okay, but if it's uniformly positive, it's okay. And if you are in higher dimension, you may also be in trouble. Okay, but in 1D, for this particular example, it's okay. and you can be you can handle much more. What you get is that U epsilon of T, these do converge uniformly to a U0 and T and X uniformly, where U0 of X is a viscosity solution of some average it's called a Hamilton-Jacobi equation, what I wrote last time, which is the integral of V over V of M of V divided by 1 minus d U0 over dt minus V d U0 over dx dv equals to 1. So which is a implicit equation for an equation for a solution U0. It must be understood in the sense of viscosity solution. I will not comment on that. Those who are interested are welcome for further discussions. And last time I told you how to get this equation. Once you know that this does not depend on V on this side, you have to do what we did last time. You have to invert rho divided by f. You have to invert to look at f divided by rho. You integrate this. This is 1, and this gives you exactly this equation. So as you see, there is a kind of averaging principle here because you have some average in V that gives you an equation. And I claim this is connected to this average here in velocity that gives you a mean velocity. Okay, here you have a mean velocity for curves, and here you can also have something which is a mean velocity of f. Okay, so this is what we saw last time, and then I raised this point that for this, and there is also a constraint which comes from the derivation that this has to remain non-negative by construction, let's say. And of course, this cannot be true except if this guy is 0 when V is possibly unbounded. If your V, your integral, your velocity set is a full line, such an expression cannot be okay. Is not compatible. It's not admissible because of course this is linear with respect to V. It cannot remain non-negative. Okay. So here, so this implies this requires V to be bounded. Okay. And maybe a last comment about the last time is that from this expression, a very similar expression, you can get the speed of propagation with branching or with growth, if you like. This is something we discussed last time. The formula was essentially the same, including the rate of growth. Okay, maybe so this, yes.
Can you tell me again why you're requiring the difference of the U-naughts to be negative?
Ah, okay. So if you think that this is a term of order 1, because there is no epsilon anymore, and you expect that U epsilon which converts to something in some sense, okay, you have derivatives, but this can be handled with viscosity solution. This will be something good. The only thing that can go wrong is when the limit inside the exponential is a positive number divided by epsilon. This will make something which is super large, and this cannot equilibrate the over term. You have an equation to satisfy, you must equilibrate all the terms in the equation.
What I was thinking is that if it's strictly negative, then it becomes degenerate as well. So it goes to 0, so it's degenerate.
Ah, no, it's okay. If it's 0, you can equilibrate. This will be just a transport equation. Okay. But in fact, the trick is that it must be true for all V and V prime. So U must be below its minimum. So U must be constant. You can reverse V and V prime in this argument. Something important for the next step. Okay, here, because it's completely symmetrical in V and V prime, you can reverse, and in fact, you get that U is a constant. So maybe there's something I'd like to spend a little time on, which might be classical for some of you, but it's important to me. I will not make the true connection between that and that. So in my mind, they are essentially the same, and they can be put in correspondence. I will make one step to this correspondence because it's important to me, but I will not do the entire thing. Okay, but I'd like to present you the dual formulation of this equation, which is very similar to that, except that I will not exactly settle it with an average velocity. Okay, but let me spend some time to explain you the duality behind this what is called the Hamilton-Jacobi equation. If you look, so there is you have an implicit equation relating du over dt and du over dx. This is what it is. You have a relationship between du over dt, du over dx. You can first observe that it is monotonic with respect to du over dt. Okay, this is actually increasing. So you can invert this implicit relationship, and you can get that du over dt is a function of du over dx, which I write like this. Okay, which is just my implicit relationship written in that way, and H has some implicit relationship. Okay, it's just a reformulation. Due to monotony respect to du. Of course, it's not monotonic with respect to du over dx because V can be positive and negative. Okay, but written in that form, it's convex with respect to du over dx. H, if you look at H as a function of what is called P, the costate variable, it is convex. Okay, so this is an exercise of implicit functions. I will not do that, but it's convex, and this is quite important for what I want to show you. So a more general setting is the case where you have an equation du over dt plus h of x du over dx. Let me introduce a space dependency in H. This can occur, for instance, when M is a function of X itself. So suppose that your change of velocity is not homogeneous in space, but you have some positions where you have some bias, for instance. Here, M need not necessarily be symmetrical. You can have bias, and suppose your bias depends on X. This has been much studied in the context of motor proteins in cells, how proteins are transported along the skeleton of the cells. And this is actually the motivation in Faggionato and collaborators problem article. You may have some X variable here. So how do you solve such a PDE in general? So you can there are several ways, but there is one nice theory, which is a theory of calculus of variation, which tells you essentially that you have a formula for this solution. So let's say the important property, the important result is that if H of X and P is convex with respect to P, as in our case, then viscosity solutions of the viscosity solution. I will assign an initial data. The viscosity solution of this equation, this Hamilton-Jacobi equation, is given by the representation formula, which is u of t of x equal to something. And this something is you have to minimize over curves such that these curves arrive on gamma t, on x. So you have your position x at time t. You have a curve, which is a candidate, gamma of s. At t, you have gamma of t equals to x. You have some unknown, some free gamma of 0 that can change. You can have, of course, you can consider many such curves, and you minimize over curves. You have another gamma here, and what you minimize is what is called the action. U of U0, the initial data of at gamma 0. So this is a problem of calculus of variation. This minimization, it's a minimization. So if you look at the minimal curve, it gives you a first order condition because it's a minimum, it's an optimization problem. You have a first order condition, and this first order condition is this PD. Okay, so this PD and this minimization problem are the same, provided that you are looking at convex Hamiltonian functions, convex with respect to the second argument, with respect to the gradient. And you are looking at those solutions, which are the viscosity solution. This can have many solutions. This is an issue, but those solutions are the good one from the work of Pierre Williams, Crandall, and Evans, and on others in the 80s. And in the convex case, you can represent them this way. If it's not convex, it's a different issue. Okay, and this is related to the large deviation principle. So I'm afraid I won't have time to explain this, how you can go from this to that. But the idea is that you solve this equation along characteristic lines. And those characteristic lines are curves, because they are characteristic. So you have characteristic curves. And those characteristic curves, you can realize that they satisfy the first order minimality condition in this problem. So if you write what a minimal curve should satisfy, you get some equations, and those equations are the same, provided that you can relate p and the velocity through the transformation. So if people are interested, I would be happy to spend some time later to do this. Yes.
You should maybe define L.
Ah, sorry, absolutely. This is why you see why it needs to be convex. So what is L? So first is a function of position on V, so Lagrangian. And what is the connection between L and H? Because L is associated with H. What you have is because P H dp x and P. So if H is convex, this is an increasing function. It has an inverse function, a reciprocal function. So this reciprocal function. So you have a function which is increasing. So there is a reciprocal function, and this reciprocal function is dl over d of x and b. So this one is also increasing, and as a derivative of a function, this function is convex. Okay, so it goes through reciprocal functions of the derivatives.
Vincent, just one thing, and then I will shut up. So maybe just the probability students in the room will be maybe more comfortable with the fact that it is the Legendre transform
yes.
of
of H.
Ah, yes, Legendre transform is more. Yes. Okay, then I will do the Legendre transform and I will do one example because it's important, of course, to do one example. Okay, so first, maybe let me start with an example. Is a case where you start from d rho over dt minus Laplacian rho equals to 0. So if you have this this equation, remember what we did is you first look at tx equals to t prime over epsilon, x prime over epsilon. Okay, if you do that, your equation becomes d rho epsilon dt prime minus epsilon square over 2. And let me do it in 1D, sorry. Yes, let me do it in 1D. Okay, I'll stick to that. This does not depend on the dimension, but just for the sake of clarity, let me do it in 1D. X square rho epsilon. Okay, you just change units, and it gives you an epsilon in front of the time derivative and a square in front of the space derivative. Okay, so as you see, it's the wrong scaling if you want to pass to the limit directly, because you will get 0 and 0 there. But this is where you change rho epsilon equals to exponential of minus u over epsilon. Okay, so this will give you minus du epsilon over dt. Here is a complicated step. You have to differentiate twice this guy. You will get two terms. So one will be minus du epsilon over dx square. One derivative square, and the next one with a minus with a sign change because of this will be 1/2 epsilon over 2 du epsilon dx square equals to 0. Okay. So this is the same step as previously. Maybe I should have started with that actually. Now what I and when epsilon goes to 0, now you are in a good shape. You will have du 0 over dt plus 1/2 du 0 over dx square equals to 0 in the sense for those particular solutions, which are the viscosity solution. You have to take care about, because here it's called a singular limit. It's the highest, the term with the highest derivative, which has been let's say neglected in the limit. But this, in some sense, remain in the limit. This should not be interpreted exactly truly as a 0, but something with sign conditions coming from this term. Anyway, but formally, at least, if you don't pay attention about the details of it, you get this equation, which is an equation rating du over dt and du over dx, very much as in my average equation here. Okay, here there is no velocity, so there is no averaging, but once it has been averaged on the persistent motion problem, you get something very similar. And now you can do the dual.
Sorry, I have a quick question.
Yeah.
What initial conditions do you take for the U epsilon problem?
Sorry?
What initial conditions do you take for the U epsilon problem?
So you take you transform the initial condition in the same way. Okay, so it might be that your initial condition for U becomes singular.
Okay.
Because of the epsilon and take the log, but this can handle singular initial data.
Okay.
Okay. For example, U can be plus infinity somewhere.
Okay.
This is possible to have initial data. Initial data is a complicated, is a true issue in this. This is why I put it under the carpet, but it's an interesting question. Okay, so what it is? So you have h of p. is 1/2 over p squared. So when you do the duality, what do you get? H prime of p is p. The reciprocal is v is L prime of v equals to v, the identity. Sorry, what I do there is sorry. So it's I call this guy v, and I'm doing the reciprocal. It's a p equals. Sorry, it's too simple to be done. So this is H prime is the identity. Is the identity, so the reciprocal function is the same in that case. So I have L prime of v, which is okay. It's this example where it's completely trivial because the function is the identity. So this reciprocal step is a trivial one. So when you integrate, it means that L of v is 1/2 of v squared. Okay, and you are left with minimizing gamma dot square, which is a usual rate function for Brownian motion. Okay, so the rate function is L of gamma dot. You have to minimize L of gamma dot, yes, which is just 1/2 of gamma dot s squared yes. Okay, and in general, the question by Pascal, in general, you have at L, X, and V is, well, again, when you write this, this is a kind of first order condition on the derivative. It's related to a minimizing a problem. It's a supremum of P dot V minus H of P over P. And reciprocally, H of X and P is the same. Formula is the Legendre transform P dot V minus L. Sorry, X is missing here. L, X, and P. Or it's a Legendre transform. It's also called a convex duality or convex conjugate. Okay, so what if I just take some distance now? What did I say? There is one case which is where some or most of you might be familiar with, is a case where you have a Brownian motion, so you have a heat equation. And if you do that step by step, you have a Hamilton-Jacobi equation for which the characteristic lines are curves, and those curves are minimizing the action, which is just the square of the speed of the curve. Something which, of course, is this is the rate function of the large deviation. So what I claim is that if you have a different rule of motion, and if you let the Brownian motion aside and you do this persistent motion, you have exactly the same type of object, but the fact that you're Hamiltonian here, and accordingly your Lagrangian, so your rate function, what measures the cost of a curve, are of a different expression. Okay, but it's the same. It's the very same idea. And this you can do it in the case where you have a homogeneous space. There is no position in your minimizing in your cost or in your rate function, or you can make it more general with a space dependence in homogeneous case. So, are there any questions at this?
Hamilton-Jacobi equation that you just wrote down. It's an interesting. It's interesting to look at what happens when you have discontinuities in solutions. Now that you have this merging of characteristics and things like that.
Yes.
And I'm just what that would mean in terms of your original model. I mean, to which phenomenon that corresponds in your original persistent motion.
Yeah. So the question is about solutions to this kind of equation. If the initial data is a convex function, they are super nice, they are smooth. Okay. If your initial data has some concave parts, or let's say something, it can make cusps in a finite time, and this cusp means that this object here is not continuous anymore. So usually your solution is continuous. I mean, you can have also discontinuous solution, but let's stick to continuous solution. But the derivative might not be, and this corresponds to the case where your characteristic lines are crossing. So you have some, let's say, overdeterminacy in your when you try to resolve your problem, and this is where you have to put some extra condition to select for the good solution, which are this notion of viscosity solution. Or here, the fact that you take the infimum here and not, let's say, the supremum or whatever. Here you choose in your optimality problem, you choose some particular thing. So in the original motivation, this can occur. I don't see much of a case where you have. So I would say maybe if you have some fronts which are in front of each other, this might you might expect to have such let's say non-convex profiles. If you have two fronts which are far away and move against each other. But apart from that, I'm not. It's not something I look at. Okay, so then my point is that this analysis up to that, in the case of persistent motion, completely breaks down if you have, let's say, a Gaussian density, velocity profile. Suppose you, at exponential time, you take a new velocity which follows a Gaussian distribution. But you can forget of everything I told you so far. It completely breaks down due to the fact that your formula for H is not well defined. You cannot define it because of this denominator, which is linear with respect to velocity. And okay, which is strange in the beginning, because you know that if you have a finite variance of the velocity distribution, you expect that in average, your persistent motion will look like a Brownian motion. So it should be close to that. But of course, when you are looking at large deviation, it's not. And it might happen that you expect that large velocities, even if they are rare because they are drawn from a Gaussian distribution, they play a significant role in the large deviation. And this is a story I'm going to tell you. But before going into that, let me say the following motivation. So let's say I think it was maybe a new section, which is a case of unbounded velocities. And then I will have the specific case of a Gaussian distribution in velocity. And the reason why I stick to this one is that now the results depend a lot on what you put there. Okay, so far it was essentially generic on M, except that you need the bounded velocities. But now it depends a lot on the details, and in particular on the tails of this distribution. So I take the Gaussian because this one is particularly suitable. And first you have my main motivation is the following lemma, which tells you that if M of V is positive for all V in R, you take any M, such for example the Gaussian, but if you should take any velocity distribution which is everywhere positive, then the front propagates with, let's say, infinite speed. By infinite, I mean arbitrarily large. Arbitrarily large. Okay, and the way you write this result is for all speed. If you look at your solution behind some moving frame with any velocity, what you will see is that your solution F will be essentially a stationary state, M of V, so there will be particles everywhere. Okay, so it means that there are particles everywhere. A field space at any speed. What do you see in simulation if you look in X? What you see if you start from something which is localized, after some time, this time equals to 0. Time equals to if you look at some time t, and if you look at twice the time t, you get something which is must, and so on. You are really you really have something which accelerates, and this is under the only condition that you can take arbitrarily large speed from your velocity distribution. You don't the matters here do not the details do not matter. And my goal now is to explain what happens in this case, and in particular to give you a rate of acceleration. You have acceleration of your front, and you are looking for a rate.
Sorry, but you still have a front, right? So that's part of your result.
No, that's not part of my result. That's part of my poor drawing. No, you expect it to flatten. Okay. For this case, I have no idea what is the scale. Yes, maybe I should write it better this way. Is it more convincing? Yeah, sorry. Okay, so what can be done? If we try to follow the same strategy, we have first to find scales. Okay, the first previous strategy was to look for t and x in suitable units to have the correct behavior. So we have to find the scale first. Second, we have to find, we have to again to look at f, which is of the form exponential of minus u of t x v over epsilon. We have to find. So this is universal. There is no change on this step. This is the same scaling, and then you have to find. We have to identify the limit equation for u 0. Okay, previously it was a Hamilton-Jacobi equation like that, but what it is, and the last one is to interpret. And get and I'm rather loose on what do I mean by interpret. It can be of several types. It can be compute particular solutions. And another way is to do the duality. Okay, to solve, because this duality is a way to solve your problem, to solve the PDE. And if you want to understand front propagation, it's a good way to solve the PDE. And in this case, I will show you at least Yeah, maybe both at the same time. But let's focus on the three first steps for the time which remains. It will be let's say rather quick because it's the same essentially the same PD. Except that there is one additional Gaussian. So which scale first? It's not completely clear. There will be something with the velocity. We have to rescale velocity now because we expect large velocity to be taken at some point in the large deviation problem. You have Wow events where you take large velocity, so you have to compute them. Okay. It's possible to do rescaling in velocity because now you are working on the full line. Before you were working on finite interval, it was not easy to rescale, but now it's okay. It's obvious you can rescale velocity. What we saw, you have to equilibrate term, okay? And to equilibrate term, you have to equilibrate this term here, which is universal. You are looking at exactly this U here.
Universal
Yes.
Zoom participants cannot see you when you.
Ah, sorry, because okay, let me write. You have to, the main point is you have to equilibrate exponential of minus U xv over epsilon and exponential of minus v. These are the two terms that you have to equilibrate in your equation. And so it's obvious that you have to rescale v. So this motivates to look as a v, which is a v prime divided by root epsilon. If you do this choice, you will have two comparable things, and okay, and this is a correct choice. So if you do that, if you rescale again t as t prime over epsilon, this is your let's say your initial rescaling, which is compatible with the 1 over epsilon here. These two things tells you that you expect x to be of x prime divided by epsilon 3/2. This is to keep, of course, what is the velocity, which is x prime over t prime. You have to. There is no choice. And okay, and you see here there is an epsilon 3/2, which will be at the end, obviously, your acceleration rate here. Okay, this will accelerate as t to the 3/2, which is compatible with that. And this is where you see that it depends a lot on the shape of your distribution. The root epsilon comes from the Gaussian distribution, and this prescribes the rate of acceleration. So of course, this is this goes all together. So now let me write the equation for u, and I will be done for today. So what is the equation for u? So equation for u. So it's pretty much the same as before. You still have minus d u epsilon over dt minus v. So this is again, there is an epsilon because you have rescale time, and there is a 1 over epsilon because you take the log derivative. Here is a bit more complicated because you have an epsilon due to the fact that you have changed x and velocity in such a way that the ratio is epsilon again, and you have a log derivative which cancels that. So but it's, at the end, it's the same. Okay, it's the same left-hand side as before. And then here there is a little subtle change. You have the Gaussian distribution, but now with a variance epsilon due to this change, which is 1 over root 2 pi epsilon exponential of minus v square over 2 epsilon. Okay, this is my change. Sorry, I should put prime everywhere because it's my new units. And I have integral of exponential as before of u epsilon tx v minus u epsilon tx v prime of epsilon dv prime, and there is a -1. Okay, so it's essentially the same as before. The only difference is this velocity distribution, which has been rescaled as well. And now, last inequality. If you try to equilibrate the terms, what do you see? Now the constraint to equilibrate terms, which is the following. So what do I need for this not to be incredibly large is that for all v and v prime, I need u epsilon t xv minus u epsilon tx v prime. But now I have an additional v over epsilon minus v square over 2. This should be non-positive. Sorry, this is in the limit as epsilon goes to 0. Again, if you believe this is a correct change of units, this is a correct change of variable, this is a correct equation, this is just a computation, and that you have to equilibrate the terms to have something tractable, then what is inside the exponential should not be too large. And if there is a uniform limit, uniform convergence, which is the case, which is compatible with continuous solutions in the limit, you have everything which is above the epsilon should be non-negative. And this tells you that this is equivalent to say that u0 tx v is less than the minimum in v prime of u0 tx v prime plus v square over 2. Okay. So this step is different from the previous one. Previously, there was no quadratic contribution. And this tells you exactly that u0 is constant because it's below its minimum. But now, being below a parabola need not be constant, u0 be constant. And this makes a lot of change. So first, there is no averaging. u0 will, it might, from this condition, and it will depend on velocity. Okay, so there is no averaging principle in the large deviation. You still have to care about the velocity profile. This matters a lot, and this exactly is very intuitive because it tells you that if you have a large deviation, a rare event, it is because you have taken a large velocity at some time, and you have to compute how much it is to take large velocities, and this will be given by the velocity profile in V. And because you have no averaging principle, it is not clear how to derive the Hamilton-Jacobi equation because you cannot average. Okay, and this is the purpose of tomorrow's lecture. What is the Hamilton-Jacobi equation behind that? It does not look like Hamilton-Jacobi equation, but it is. And what is the dual formulation? What is the rate function associated to that? And this is for tomorrow. Thank you. All
right, any questions?
Yeah, thanks, Vincent. If I understand well, so if the set of velocities, or well, the space of velocities is bounded, then particles all the time they switch velocities at the time scale of order 1, right?
Yes.
And this gives an averaging, and it's not good. It's not a good strategy to try to keep the velocity for a macroscopic time period. And here they keep it for a macroscopic time period.
They do,
right?
Yes.
And so can you describe it a little bit more? So will it be, for example, if you want to get something into space, will it be just basically one particle traveling there during the whole time? Or?
So it depends on the dimension.
Okay.
So in one dimension, for the Gaussian, a large deviation means a particle which has taken a large velocity one time. It has kept for a long time because you have rescaled time. So keeping it for a time of order t prime means keeping it for a very long time in t. So it has kept it's two rare events. It's taking a large velocity and keeping it for a very long time. So it's a combination of these two, and then it arrives to a point and then it stops there. So it's only one single very large jump in one dimension. In 2 dimensions, you can have more complicated processes depending on how you start with, because everything now depends on the velocity. So when you do your minimization, you also have to take care of the initial velocity of your distribution, and then you may have complicated combination where you go in one direction and then you switch to another one, and sometimes you make some pause. Okay, but in 1D, as we will see tomorrow, is essentially one large jump, which means large velocity and long time to arrive to the farthest point. And you see it exactly. What is interesting is that the stationary solution. Okay, it's too long for today, but you see it on what is the U0 in the limit, something which is very different from the Brownian motion. We'll discuss more tomorrow about that.
You had this lemma about if m is positive, then you have these acceleration. This acceleration. Can you just say a few words about how you would prove that?
Yeah. Is it similar? No, it's not there. So the result is that if m is positive, then you have acceleration. Let's put it this way for over here for all. The point is it's all about the dispersion relation. The dispersion relation gives you velocity out of shape. So you have this dispersion relation. It doesn't tell you that lambda c is h of lambda, but this is for a bounded v. Because this can only be defined for so what do? Is first you truncate that, and then you have a comparison principle because you have omitted a large velocity, and this is for your good. So you truncate this guy for a large set of velocities, and then you look at this, and you see that what will happen when this is a truncated function associated to that. What will happen is that certainly this will select a large speed. Otherwise, there would be a way to save this relationship. But what I did not say, what is behind is there is absolutely no way to save this for large velocity. There is no way to make it, to reformulate it in such a way that you can handle it. There is no way to save it. And this is essentially what tells you this result. And this is related to what I will discuss tomorrow. So there is no possible way to save it. It tells you that when you truncate m and you look at the truncated h, c, the minimal speed is going to infinity. And then you can construct sub-solution and you can push your front at any speed.
So you don't get anything quantitative, I guess.
Yeah. But it's difficult then to get a rate. And this is what we did this stuff. Yeah.
So the thing I find surprising about this maybe is that this does not depend on the tail behavior of m.
Absolutely. No. The rate of acceleration will see the tail, but the fact that the minimal speed is plus infinity is not related to the tail. As soon as you can take large velocity, you can just travel fast. And this was surprising for us as well.
Yeah, it's kind of amazing because you have non-local Fisher KDP, right, where there's this cutoff and when you have acceleration for some people. Okay, any other questions? Otherwise, I guess it's the coffee break, and it's probably best to not keep you from coffee for too much longer. So let's thank Vincent one more time.